number of basic groups, that's a parameter that is vastly different between the two sets. If simple, not simple, if many compounds in the atomic domain pick at one basic group, the Bayer compounds are quite different. The average and the highest number of, the highest abundance of basic groups peaks around 4. Thus, the industrial compounds are much richer in basic groups. And finally, in terms of the fraction unionized at pH 7.4, the industrial compounds are a bit more neutral at this pH than the topic set. So let me switch to the model itself and say what is so special about the model that enables the expansion to the industrial applicability domain with such efficiency. Well, first of all, the model is thermodynamically accurate. We modeled the polyphotic ionization of compounds with complete detail, with complete microscopic detail. So let me illustrate what that means on this simple example. Probably when you learned about ionization of organic molecules in school, you were told that they ionize sequentially. In other words, you can assign the observed pKa value to individual functional group. So if you have this simple dicarboxylic acid, 1 pKa would correspond to one group and another to another group, which means that the ionization occurs sequentially. One group protonized than the other, and so on. Well, this view is actually incorrect. The next slide shows that because of the equivalency of both carboxylic groups, the first proton can bind to either one of them. And there is a 50-50 chance that this event will occur. So you may think, okay, well, there are two separate routes of protonation, not just one. And you may think that this is because of the molecule symmetry. No, it's not. The broken symmetry only changes relative percentages, relative probabilities of proton binding, not the qualitative picture of binding. There are still two distinct routes of protonation, and that's the exact picture. In general, with molecules, for molecules with n-ionizable groups, the problem of protonation is a simple combinatorial problem. Distribute k protons among n sites. N sites on the right side, you have k protons, and you simply have a simple mathematical problem of distributing those protons. There's n over k, there's Newton's symbol n over k, distinct combinations. On the next slide, I show the example with n equals 3. If there are 3 ionizable groups, you are able to distribute protons in 8 distinct ways. So let me define a few crucial concepts here. On the left side, you see the column showing the number of proton bands. If you know that there are k protons somewhere, you know about the specific ionization macrostate. We call them macrostates. A macrostate is simply knowing there are k protons somewhere, and the k can vary from 0 to 3. On the other hand, if you know where the protons are bound exactly, you have an intimate knowledge of a microstate. So, for example, when you have one proton bound somewhere and you know exactly where it is, and there are 3 distinct possibilities, then you have a complete knowledge of microstate. This is a concrete, let me wait for the next slide, there we go. This is a concrete example. 3-protic molecule cetirizine has been measured in this work published in 2009. The slide shows measured percentages or measured relative percentages that specific microstate contributed to a given macrostate. So the microstate with 1 proton is dominated by a state where the middle nitrogen is protonated, 99.1%. When 2 protons are bound, there are 2 dominating microstates, one with the carboxyl group protonated and again middle nitrogen, and the other with 2 basic nitrogens, whereas the carboxyl group remains deprotonated. So it's not always true that only single microstate dominates. It could happen, and it happens quite often, that more than one ionization state is important. The individual transitions between microstates are called microequilibria, and each microequilibrium, which elementary deprotonation event carries its own equilibrium constant. We call them microscopic pKa values. So you can see a network of 12 microequilibria on the right side, and the corresponding measured macroscopic pKa values. These 3 values can be measured in the standard titration experiment, and they are statistical averages in the logarithmic sense of the microscopic pKa values on the right. All right, so with that picture in mind, let me describe the mechanics of modeling. It's really simple. We identify an ionizable atom in a molecule. We calculate the vector of numbers for that atom. We calculate it from its chemical properties, physical properties, and so on. We call them atomic descriptors. They include the atom itself and also its molecular environment. So they are sensitive to what's happening all over the molecule. Currently, we have a set of 140 atomic descriptors per atom. We choose optimal subset of those atomic descriptors to predict microscopic pKa values. Here are some examples of atomic descriptors. There you go. For cetirizine, I listed just 4. There are electrotopological states, the partial atomic charges, polarizabilities, and hydrogen bond basicities, and so on. So there are a lot of other descriptors that use pKa model. How do we use these descriptors? It's very simple as well. We use artificial neural network ensembles. You can see the picture on the right, neural network attached to every atom of cetirizine. And they carry distinct colors because different networks are used for different atom types. We have a total of 10 neural network ensembles for 10 classes of ionizable atoms. So, for example, we have a network ensemble for hydroxy acids, we have a network for amines, and so on. Okay, all these 10 classes are covered, even as exotic classes, carbon-based bases. As I mentioned before, the inputs for those elementary models are atomic descriptors, and they predict ionization microconstants. After the microconstants are predicted, the observed microconstants are calculated from microequilibria theory. Let's go to the next slide. It's quite The model was trained, as I mentioned, on the set of about 33,000 pKa values. And this slide illustrates the model performance on the training set, as well as on the test set that we set internally. We set it aside. We don't use it for model parameter training at all. We set it aside to validate the model. The training pool consisted of 25,500 pKa values, and they were split along the following lines: about 10,000 from public sources, about 15,000 from Bayer Pharma. The internal test set was also split at a similar ratio, about 3,600 from public sources and 4,500 from Bayer. The statistics is illustrated in color for the train verify subset as well as for the test set. When we see that the statistics of the two subsets match, and they do in this picture, we know that the model is validated and it is not overtrained. Many models were built, and the internal test set was used to select the best model. Well, as I mentioned before, for a given macro state, there is quite a large number of different combinations of available microstates. It turns out that if you add all of them for all ionizable states, the number of microstates, or we call them microspecies on this slide, or microequilibria, is exponential. It's an exponential function of the number of ionizable groups. For example, if you have 3 ionizable groups, the number of species is 8, as you saw on the previous slide, and the number of microequilibria is 12. Not too bad, but when the number of ionizable groups increases to 20, we have to deal with over 1 million microstates and over 10 million of microequilibria. Thus, in order to process such a large molecule, with so many ionizable groups, we have to have a very fast algorithm, which we have. This performance was measured at Bayer. Okay? So this was on the Intel Core Duo CPU. On average, the algorithm processes 3,540 microscopic pKa per second. So the practical limit we set in the program is 20 groups. Bayer lowers it to 14 in order to process it faster. And Mario told me they have seen, on average, okay, if you take just all sets and so on average, they have seen performances of about 100,000 compounds per hour. This is quite good, I would say. So while I wait for the next slide, let me switch to Mario, who will talk about the ways that the Bayer measured pKa values. Mario?
Yeah.
The floor is yours.
Yes. Okay. Okay. So, yeah. Yeah, I'm on the right slide. It's strange. I saw that. Sorry, everyone. I thought I had, yeah, change. Just a moment.
I think you're on the right slide. I see expression.
Yeah, I'm on the slide, but if I go into presentation mode, it's not doing anything right now.
If you want, I can switch to mine.
Switch for a moment back to your to control at your place, because for some reason I don't get access to my presentation.
Okay, I switched back to myself. And,
yeah.
There you go. The screen is loaded. So you can go ahead.
Yeah, let's continue at your place. You take control and I tell you when to switch the slides. I don't know why it is, but somehow my PowerPoint doesn't react anymore. Okay, so at Bayer we use a series T3 system for pKa measurements. The T3 can measure 1 pKa in about 4 minutes. Before the measurement starts, it is important to categorize the compounds into acids, bases, zwitterions, and compounds which do not contain any ionizable groups in the measured pKa range of 2 to 12. This means that our experimentalists also need a good pKa prediction tool in order to set up the measurements properly. Next slide, please.
Okay. So
it doesn't matter. At Bayer, we have investigated the experimental variations inherent in our pKa measurements. First, we asked the following question: how large is the natural spread inherent in the experimental method? To answer this, it has been investigated by how much measurement results deviated on average in the years 2012 and 2013 up to now, for the two internal standards measured in Wuppertal on the latest instrument. We found that the natural spread is plus minus 0.06 for diclofenac in 73 measurements and plus minus 0.05 for warfarin in 84 measurements. So the natural spread for our reference compounds measured on one particular instrument in one location is quite low. Over time, of course, we have measured pKa on old and new instruments and in different locations in our research sites in Wuppertal and Berlin. We also measure sometimes different batches or salt forms of the same chemical entity. This is a real-life data pool from which the pKa data sets for training and testing have been sourced. We therefore also analyzed the natural spread inherent in those data sets. For this, it has been investigated by how much measurement results deviate on average if compounds with identical canonical spiles of the chemical entity of their salt mixture-separated structures are measured multiple times. And we found a natural spread of about plus minus 0.1, which is a little bit higher than the spread for the two reference compounds, but still quite low. We can therefore state that the experimental consistency of the pKa measurements at Bayer is quite high. Now, Robert attempted to investigate the experimental variations inherent in published pKa measurements, and I let Robert explain this slide to you now.
That's correct. You're right. The literature data represents 100+ years of experimental measurements published in the literature. To my knowledge, there's no systematic study that would investigate the natural spread or the intrinsic spread of the measured pKa values. As you know, the measurements can vary all over the place in terms of quality. Fortunately, there's a book on the market. Richard Prankert has published a very nice book in 2007, which resulted from an enormous amount of work he put into extracting pKa values from the literature, extracting the methodologies, and evaluating the methodologies in terms of the quality. So his book contains about 600 pKa values measured at highest quality. And the highest quality is defined here as a experimental precision no more than 0.04 log units, or experimental precision better than 0.04 log units. Well, experimental precision is not the same as experimental consistency. I think many of you are aware of that fact. If not, let me illustrate it by this example of 3 compounds. These are the 3 compounds measured with the highest quality. Their pKa values were measured with the highest quality. Each of the values shown in the middle column has precision better than 0.04 log units. And naively you may expect why the predictive model doesn't have this kind of accuracy. Well, this is because the values come from different labs, and there are deviations, even though they are very precise. The deviations between individual values are quite large. They can vary from 0.2 log units to as much as 0.67 log units. Lidocaine, and as I said, each of the pKa's for lidocaine was measured very precisely, received the highest grading in terms of the quality of the experiment, and so on. Nevertheless, they can differ by the virtue of being measured by different groups in different labs by as much as 0.67 log units. At this moment, I will hand the presentation back to Mario, who described the end-user applications